We've talked about the concept of electrical equivalence a few times in this class. But what I mean by electrical equivalence in a more formal sense would be that if we took the following network where we have some voltage Vs and apply that voltage to a network containing two resistors in series, let's call it R1 and R2, we could observe a voltage drop VL over those two resistors in series and a current IL flowing through those two resistors in series. We found that that resistor network was electrically equivalent to a single resistor Req is equal to R1 plus R2 where this voltage drop VL and this current IL would be identical in both cases. Okay. We could develop a similar thing for resistors in parallel, voltage sources in series, current sources in parallel, etc. The key here is that for these two networks to be electrically equivalent, they need to experience the same voltage drop VL across their terminals, and they need to experience the same current IL flowing into their terminals. So what we are going to do today is prove that this network let's call this VS in series with some resistor RS is electrically equivalent to this network containing a current source IS in parallel with a resistor RS under a very specific set of conditions. Okay. The circuit on the left is what is called a practical voltage source. And our circuit on the right is a practical current source. So if we look at the model here for a practical voltage source containing an ideal independent voltage source in series with some resistor RS, what do you think the resistor is doing? Anybody have any thoughts? Bradley.
So if all the resistors are in parallel, then the voltage drop across them is the same.
So what you said is true, but there's only a single resistor here, so I'm not following your logic. What are resistors used for? Pardon? So they do absorb power. All right, first day of engineering 120. You guys connected a resistor in series with an LED and then applied 5 volts and then no volts and then 5 volts and then no volts over and over and over again to make the LED blink. Why was the resistor there? To not burn out the LED. How did it not burn out the LED? decreased the amount of current that was able to flow. Exactly right, okay? So for an ideal voltage source, by itself, is there a constraint on the amount of current that can flow through this? None whatsoever, right? We could have an infinite amount of current flowing through this guy, right? So there's a limitation in our model here, and it's best described if we tried to connect our ideal voltage source to a short circuit, because that's absolutely something that we can do in practice, right? We could take a battery and we could strap a wire from the positive polarity terminal to the negative polarity terminal. Not a particularly good idea, but we can absolutely do it. We can observe the effects. The effects are that that battery is going to send as large of a current as it possibly can through that wire, creating sparks and all that kind of good stuff until all of its energy is dissipated, right? But for an ideal voltage source, we face a conundrum where the voltage drop across our short circuit is 0, but it's also Vs at the exact same time. And the only way for that to be true is if the current I is infinitely large. So if we put a resistor in series with that voltage source in our model, what it does is it restricts the amount of current that could possibly be supplied by that voltage source to some finite value, making it behave like a practical or real voltage source, okay? We could run into a similar situation so let's say that we have a current source, an ideal current source. IS like so. Well, what's the voltage drop over the current source in this configuration? It's got to be infinitely large because there's a current flowing through an infinitely large impedance, right? So in this case, V would be equal to infinity, which obviously can't happen. So putting the resistor in parallel with our ideal current source gives us a path for that current to flow through that isn't the infinitely large impedance, therefore restricting the amount of voltage that can appear across the current source's terminals, okay? So these practical voltage sources and practical current sources are used as a better model to understand the behavior of real world circuits, okay? Now they are related to each other in a very interesting way, okay? So let's look at a practical voltage source circuit here. Let's say we have some voltage Vs. Some resistor Rs, and a set of open circuit terminals. And then out here, we apply some load resistance RL, where the voltage drop over our load resistor is VL, and the current flowing through our load resistor is IL, okay? So if RL were equal to 0 ohms, IL will be what's known as the short circuit current, ISC. What value will this short circuit current have? Symbolically, right? We don't have any numbers or anything here, but what should it be? I disagree. I disagree wholeheartedly that it will be infinity. VS over RS. Exactly right. VS over RS. So this short circuit current is one of the parameters that defines a practical voltage source. Just as a quick aside, if RL is equal to 0 ohms, how much power is absorbed by my load? Pardon? I disagree. So if we have a resistor, we know the voltage drop over the resistor or the current flowing through. So let's say we have the voltage drop over the resistor, okay? V squared over R. Well, in this case, the voltage VL is 0 because our RL is a short circuit. So we have 0 squared divided by the resistance of 0 ohms. So I would argue power absorbed should be 0. Another way to think about it, if RL is 0, VL is 0, and so VL times the current has to be 0 as well, right? So when we short circuit this guy, we're not delivering any power to our load resistance, which means all of the power that's being supplied by our independent ideal voltage source VS is being converted to heat by its internal resistance, so that this practical source as a whole supplies no power because the load isn't absorbing any power, right? What if RL were equal to infinity? So this is how we determine what's called the open circuit voltage. So if RL were an open circuit, what voltage drop would appear across the terminals of our load resistance? I also disagree. Okay, so we're saying that this guy right here is infinity ohms, or an open circuit. So what we're looking at is that. It won't be 0 because there's no current. It'll be VS because there's no current, right? If no current is flowing through that resistor RS, there is no voltage drop over the resistor RS. So simple application of Kirchhoff's voltage law should tell us that VOC is simply VS, right? Right KVL around the loop, prove it. So from those two data points, we can actually develop a graph. It's called a load line graph, where we plot IL measured in amps versus VL measured in volts. And it's going to look something like this. This is our short circuit current. This is our open circuit voltage. And the slope here is 1 over our source resistance of RS. This tells us effectively how our circuit is going to behave if we connect it to literally anything, right? Anything that has an impedance ranging from 0, or excuse me, a resistance ranging from 0, which is a short circuit, which is where we have that ISC over on the left-hand side, all the way up to an infinitely large impedance, like an open circuit, and we see that our current falls down to 0, and we're at an open circuit voltage, okay? This simple linear graph tells us everything that we could possibly ever want to know about the behavior of a practical voltage source, okay? While we're at it over here, how much power is absorbed by my load when my load is an open circuit? 0, because no current can flow. Absolutely right. We can develop a similar set of relationships for a practical current source. So let's say that we have some current IS in series with some resistance, excuse me, in parallel with some resistance RS. I apologize for my flub. And this is my current I sub L. So let's say if RL is a short circuit, and IL will be our short circuit current, which in this case should be what? Pardon? IS. All of the current will flow through the short circuit. And our power absorbed by our load will be 0. If we have an open circuit, VL will represent our open circuit voltage, which will be what in this case? IS times RS, exactly right. And we can see again that our system is characterized by a short circuit current and open circuit voltage and the internal resistance of the source RS, giving us pretty much an identical graph. All right. There's IL measured in amps, VL measured in volts. Here is ISC, here is the OC. So these two practical sources behave identically. They're quantified by that open circuit voltage, that short circuit current, and that resistance RS. So now that we understand that those practical sources behave identically, let's see what makes them electrically equivalent, okay? So let's take our practical voltage source model where we have VS in series with some resistance RS. We apply some load resistor RL. We have VL And we have IL. We take our practical current source model, where we have IS in parallel with RS. We connect an identical load and our goal here is to determine under what conditions VL is identical in both circuits and IL is identical in both circuits. So let's look at the circuit on the left. What should my current IL be? In terms of these quantities. Exactly right. Application of Ohm's law tells us that we'll have Vs divided by Rs plus RL. We come over to the right-hand circuit. We can use current division to find out how much current will flow through that resistance RL. So that's going to look like IS multiplied by 1 over RL divided by 1 over RS plus 1 over RL, which with a little bit of algebraic manipulation is going to look like IS times RS divided by RS plus RL. So, under what condition are these two currents the same? When Vs is equal to what? Exactly right. These two are electrically equivalent when our source voltage Vs is equal to our source current Is times that internal resistance Rs. So what that means is that anytime I have a voltage source in series with some resistance Rs, I can replace it with a current source having a value of Is, excuse me, Vs over Rs in parallel with Rs, or anytime I have current source Is in parallel with some resistance Rs, I can replace it with a voltage source Is multiplied by Rs in series with some resistor Rs. These are our source transformations. Okay. So this is a way for us to simplify circuits in very specific conditions. Anytime we have a voltage source in series with a resistor, we can replace it with a current source in parallel with a resistor, if that would help our analysis. Similarly, anytime we have a current source in parallel with a resistor, we can replace it with a voltage source in series with a resistor using these rules. Connor.
So when we're going from voltage to current source, is the point of the arrow always going to be on the positive terminal?
Fantastic question. You're absolutely correct, okay? So if our arrow, if our positive polarity terminal is on top, the arrow should be pointing up. The positive polarity terminal is on bottom, the arrow should be pointing down. Positive polarity terminal is on the right, the arrow points to the right, etc. Same thing for the other transformation. When the arrow, whatever side the head of the arrow is on gets the plus side, whatever side the tail of the arrow is on gets the minus side. Fantastic question. So our rules here, pretty straightforward. So let's work an example problem that illustrates how to properly use this tool. Okay. So, bless you. Let's say that I have the following circuit. So that I have a 2 ohm resistor here, 9 ohm resistor. I'm going to call this voltage Vx, 1 amp source over here. All right, my ultimate goal in this problem, let's say, is to determine that quantity Vx. Okay. So let me ask you guys a question. How many nodes does this circuit have? 5. How many meshes does it have? 5. 5 nodes and 5 meshes. Okay. So are there any simple resistor combinations or anything that we could do to make this circuit easier to analyze? No, none of the resistors are in series, none of them are in parallel. So before we learned about the concept of source transformation, this problem would seem like it's something that we could never analyze on test or something like that. But we'll find that we can easily get it to be something that we can analyze with our calculators or whatever, getting it down to a 3x3 system rather easily. If we follow through long enough, we can actually make this guy a single loop circuit that we could have analyzed on the second day of class. Take some time for sure, but we could get there, okay? So since I don't have any voltage sources in this circuit, I think it's pretty fair to say that we have 0 practical voltage sources that we could transform. How many practical current sources do we have? 3. Because the dependent source is in parallel with a resistor, so I can still form a practical current source with it, okay? So what I'm going to do here is I'm going to label some terminal pairs. We'll just worry about these for right now. Okay? The reason why I'm labeling these is because I want to burn into your brain the way to do this properly, okay? So how we are going to treat this operation of source transformation is we're going to disconnect the practical current source, transform it, and then reconnect it using the same set of terminals. So this tells us exactly where it's supposed to go when we put it back in, because sometimes circuits can be drawn oddly, as I'm sure you guys have noticed on your web work and things like that. And so understanding the rules of how to apply this technique is very important. Because if you do it incorrectly, then you're obviously going to cause some errors in your analysis. So let's look at that practical current source on the left. We have a 5 amp source in parallel with a 3 ohm resistor. So what is that going to transform into, Abigail? What does my practical current source transform into? So I take this 5 amp source and this 3 ohm resistor out and perform a source transformation. I will get a voltage source in series with a resistor, right? So what should the value of the voltage source be, Abigail? Five amps times 3 ohms is 15 volts. What value should my resistor have? Exactly right, just stays the same. So if it was a 3 ohm resistor, it stays a 3 ohm resistor. Okay. So now I can literally just erase this guy. And replace it with a 15 volt source in series with a 3 ohm resistor. So I've just eliminated a mesh. I just made this circuit easier to solve, right? Now, one other thing that I did, besides eliminating a mesh, was now we can see that the circuit is behaving as if the 3 ohm resistor is in series with that 4 ohm resistor, which means we could combine those two resistors and eliminate a node while we're at it. If we were so inclined, my nose is itching like crazy, I apologize. We could convert that practical voltage source back into a practical current source using the different resistor value, which would put that 7 ohm resistor in parallel with our original 7 ohm resistor, and we could eliminate another something, right? So we would effectively, if we did that source transformation, we would be adding a mesh back in, but then we could combine those resistors. We would be adding a mesh to eliminate a node, but then combine the resistors to eliminate the mesh we created. But let's not worry about that right yet. We have that practical source on the right, where I have, bless you, a 9 ohm resistor, excuse me, yeah, 9 ohm resistor in parallel with a 1 amp source. I can replace it with practical voltage source where what should be the voltage of my new practical voltage source? Pardon? 9 volts. So just 9 ohms times 1 amp gives me 9 volts. My 9 ohm resistor stays the same. Does it matter if I put if I switch the position of the voltage source and the resistor? No, not at all. When two elements are in series, they're interchangeable. When two elements are in parallel, they're interchangeable. So it doesn't particularly matter if I drew this as nine volts in series with a 9 ohm resistor like this, or if I move the 9 ohm resistor down to the right, effectively swapping the position. As long as I get the polarities for the voltage is correct, it doesn't matter in the least what order I put it in. So that second source transformation eliminated yet another mesh, which means we are at a place where we could easily solve this guy using mesh analysis, right? 3 meshes, nothing particularly difficult here. We do have that dependent current source in the middle, so we would have to do a super mesh around it. But other than that, we're back to something that we could easily analyze and all that kind of good stuff. So this concept of source transformation can be a very, very powerful tool in simplifying circuits. And it's actually fundamental to what we're going to be covering when we get back from the break, which is called Thevenin and Norton equivalent circuits, which is a way that we'll discover where we can make any two-terminal circuit or network look like a practical voltage source or a practical current source pretty quickly and easily. All right, so how do you guys feel about source transformation as a concept? Pretty straightforward, right? The rules are fairly simple. Give yourself some terminals, disconnect what you're trying to transform, and then reconnect the transformed thing, okay? So now I want to talk about the concept of maximum power analysis or maximum power transfer, okay? And understanding the behavior of practical voltage sources and current sources can actually make this pretty powerful tool, okay? So let's say that I have a voltage source Vs connected to a resistor Rs. So I have my practical voltage source. This is my voltage VL. This is my current IL, right? So we could see pretty easily that IL is simply Vs divided by Rs plus RL. And we can see that VL is simply Vs times RL over Rs plus RL using voltage division. Everybody okay thus far? The power that is absorbed by my load resistance is simply the product of IL and VL, which would look like Vs squared times RL divided by Rs plus RL. And so for a given value of Rs, if we plotted PL as a function of RL, we'd get something that looks like this. should be parabolic in shape, okay, roughly. Where we know that when RL is equal, yes. You are 100% correct. Thank you. Thank you very much for that. Yes, absolutely, it should be squared. Thank you. So when RL is equal to 0, we have a short circuit. And we determined earlier that when we connected a short circuit to a practical voltage source, no power was delivered to the load. When RL is getting really large, like close to infinity, we know that the power absorbed by the load should be something close to 0. And then this graph covers all points in between. Well, this location right here is when maximum power transfer occurs. Okay. So let's call this guy right here E max. And this is the value of RL that we're trying to figure out. So we could, if we wanted to, take the derivative of PL with respect to RL, and set that derivative equal to 0, and solve for the value of RL that makes that happen, right? That's what you guys learned in calculus. Whenever you want to minimize or maximize a function, you take the derivative of it, and then you set it equal to 0. Well, if we do that, we find that maximum power transfer occurs when RL is exactly equal to the practical source resistance RS. And therefore, E max is Vs squared times Rs over Rs plus Rs squared, which simplifies to 1/4 Vs squared over Rs. What do you think the maximum power that can be transferred by a practical current source will be? So let's say that we have IS in parallel with RS in parallel with RL. Here's VL, here's IL. So using current division, we'll find that IL is IS times RS over RS plus RL. This is what we, let me scroll up here real quick. This is the result of algebraic manipulation of our normal current division equation here, okay? So I just wanted to show you where it was coming from and all that kind of stuff. VL would just be IS times RS and RL in parallel. And so power absorbed by my load is going to be IS RS quantity squared times RL over RS plus RL, quantity squared. Well, if this practical current source here on the bottom is electrically equivalent to that practical voltage source up there at the top, meaning that they have the same value of RS and we're connecting it to the same load resistor, then that VS squared up top is just exactly what IS times RS squared is representing down here on the bottom. So we know that maximum power transfer is going to occur whenever RS is equal to RL, because we are maximizing literally the exact same equation, right? So if we make that substitution where RL is equal to RS, we find that Pmax is just 1/4 IS squared multiplied by RS, which is literally the exact result we would get if we substituted in VS is equal to IS times RS. So that is maximum power transfer. Now let's tie everything together and work an example problem. And then I'm going to stop talking for the day. Let's say that we have this circuit, a 12-volt source in series with a 3-ohm resistor, in series with a 6-ohm resistor, in series with a 7-ohm resistor, in series, sorry, these aren't all in series, with a resistor RL, like so. And we want to know, A, what value of RL will absorb most power, and B, what that maximum power is. So effectively, I'm asking you guys to apply the maximum power transfer theorem to this circuit, which isn't a practical voltage source or a practical current source. Okay? So the key here is how can we make everything that's connected to that load resistor RL look like either a practical voltage source or a practical current source? Because once we can do that, we just get to simply use an equation, right? So who's got some thoughts? All right, so let's slow it down a smidge. So we have a practical voltage source on the left-hand side of these terminals. Carter's suggestion is that we turn that into a practical current source. So Carter, what will that practical current source be? All right. Carter says 4 amps. I have included direction up in parallel with a 3-ohm resistor. Is everybody okay with that? All right. Henry, what should we do next? Sure. So the 3 ohm resistor and the 6 ohm resistor now appear to be in parallel, so we can do that combination. So it's 3 in parallel with 6. 2, right? 3 times 6 over 3 plus 6, 18 over 9 is 2. I'm going to take this guy out, and I'm going to replace this guy with a 2 ohm resistor. Okay. David, what will we do from here? So we can disconnect this practical current source and rewrite it as a practical voltage source, where we will have a voltage source, which you say is 8 volts, and I agree. Will be in series with 2 ohm resistor, in series with 7 ohm resistor, in series with our resistor RL. Mr. Darbone, what can we do now? All righty. Combine the 2 resistors, so 2 plus 7 looks like 9 to me. So we're now able to answer question A. What value of RL will absorb the most power? Jessica. The maximum power transfer occurs when our load resistance is equal to our source resistance, RS. Well, in this case, RS is just 9 ohms. So maximum power transfer occurs when RL is 9 ohms. Part B, our maximum power will be 1/4 times Vs squared. So that's going to be 8 volts quantity squared divided by RS, which is 9 ohms. So this looks like 64 over 36. And if you want to simplify it, by all means, go ahead. All right, so that is enough out of me for today. There is an in-class assignment and all that kind of good stuff, so feel free to start working on that. If you have any questions about anything, I'd be happy to